With some multiple choice questions, looking at the applications of the derivative. So I'm going to switch our mode a little bit because I want you to, our layout actually, I want you to see the calculator that I'm using because it's very important. I'm going to be using the calculator back and forth with these questions. Um, and let me switch just a little back so you can see the questions first. But we're going to be looking at, we're told that the derivative of the function is given by this equation. How many points of inflection does the graph of the function have on the interval from -2 to 2? So something to note is that when the first derivative has a max or a min, then that means that the function has a point of inflection. So what we're looking for on this graph are maxes and mins, and we have to be sure that it falls within this interval -2 to 2. So I'm going to switch our view to the calculator, Desmos Calculator. I'll link it below in the description so you can see it. And let's put in our equation for the derivative. Well, I didn't use my right arrow to get us out of the exponent. There we go. And it goes crazy. Okay. However, I want you to see all we need are the number of maxes and mins. There's 1, there's 2, there's 3, 4, and 5. And that's how I get that there are 5 points of inflection on the function because there are 5 maxes or mins on the graph of the derivative. So I'm going to switch this back. And so we should get 5 on this one. Okay, let's take a look at the next question. A right cylinder is such that the sum of the height and the circumference around the base is 30 centimeters. What is the radius that produces the maximum volume? So we're trying to maximize the volume. That's going to be our primary equation. Because there are two variables in the primary equation, we need a secondary equation to help us. So that secondary equation is coming from that first sentence. We're told that the sum of the height and their circumference, so height plus circumference is 30 centimeters. Now we want to eliminate the height, so we're going to solve this equation for the height by subtracting 2 pi r, and we're going to substitute it into our primary equation. So we've got 30 minus 2 pi r. Now, since we've got it down to one equation, let's go ahead and distribute the pi r squared. That'll make it just a little bit easier. And yeah, that is pi squared. It'll make it a little easier to take our derivative. So our derivative becomes dv dt equals 60 pi r minus 6 pi squared r squared. And then when we try to maximize, we want to set this equal to 0. And I know right now that pi squared looks really awkward. I'm going to leave it though because I want to, you'll see where one of them is going to cancel out. I'm going to bring this term to the left only because I want to make it positive. And then I'm going to divide both sides by 6. I'm going to divide by 6 pi squared r. I had to think about that and get it all out. There we go. Pi squared r. So obviously everything but one r is going to cancel here. But over here I'm going to be left with 10 on top, pi on the bottom. 10 over pi, and that's centimeters. And that is answer choice E here. Okay, let's look at number 3 then. A particle moves along a straight line such that the velocity is given this. What is the acceleration? Now on this one, you may or may not have done your derivative rules for having an exponential yet. And so this question really, really wanted you to find the derivative on the calculator. So I'm going to switch our view over so that we can see Desmos, and you're going to be able to see that I've already typed our velocity into Desmos. Now, Very important. In order to get Desmos to do the value of the derivative, you have to label this as the function, or you may have to label it as the first derivative. Because when I call for the derivative of this in the next step, that's where I want to use that f prime notation, and I wanted it at 3. And you can see that Desmos will give me the value that I want for it. So I know that the acceleration at 3 is equal to the derivative of the velocity at 3. And so I put this into Desmos, and that's how I get answer choice B here. So again, this question was not meant for you to take the derivative of that. That's not a calculus AB, AP level content that they want you to memorize those rules. This wanted to know if you could take the derivative of the on the calculator. So let me put our view back. Let's look at number 4. A particle's position is given here. We want to know when, or we want the total distance between 0 and 3.5. So if you'll remember, total distance is the distance traveled without regard to direction. So the first thing you have to do is to find the velocity by taking your derivative. And then we have to find out when that's equal to 0 on this time interval. So I want you to go to your Desmos calculator again. I'm going to take off this one and this one, and I'm going to put in 3 plus 4.1 cosine of, you can do it of t or of x. Actually, I think you have to do it of x here for this one. And we're going from 0 to 3.5. So it looks like that it changes direction right there. So we know that our only turning point is at 2.392. Now, what we have to do then is to do the change in position from 2.392 to the beginning. And then we also have to find the change in position from 3.5 minus 2.392. So basically from the beginning to the turning point, calculate that distance. I'm using absolute value to take the direction off of it. And then I'm going to calculate the distance from the turning point to the end. And then I will do the absolute value of that again. And then I will add them together. So just like before, I'm going to go ahead and go back and put the function in here. And let me do that. 3t plus 4.1 sine of t. I got to put parentheses around it. I forgot. And then, oops, I put t's instead of x's, and I need a 3x. There we are. Okay, so I'm just going to put my values in here. 2.392. There we go. That's my position. I can ask the calculator to give that to me. And let's see if I could be real tricky here and put f of 0. See if it'll, oh, look at that. It will do that value for me. Pretty nice. I get 9.969. Now remember, I'm going to have to do the absolute value myself. So I'll put 3.5 minus f of 2.392. And I'm going to take that negative off because I know I need the absolute value. And I get 0.908. Now, friends, you can add these together and you're going to get answer choice C there. Okay. Be real careful that you use your absolute values, though. But Desmos is a nice tool to be able to find those values for you. Okay, let's keep going. I'm going to switch our view back so you can see. Number 5 says the function is continuous and nonlinear for this interval. We're told that the endpoints are not equal to each other. One is 5, one is -5. If there is no value where f prime of c equals -1, then which of the following statements are true? So you've got to go back to your theorems. There's 2 theorems that guarantee us a value for the derivative. One is Rolle's theorem that tells us with some conditions that the derivative will equal 0. And there's mean value theorem, which tells us that the derivative with some conditions that the derivative will equal the slope of the tangent line. I'm sorry, the derivative will equal the slope of the secant line. Now, we're dealing with mean value theorem here. So we're told that it's continuous. The other criteria for mean value theorem is that the derivative must exist. And so that is what's failing here is that the derivative, there's got to be a place on here where the derivative does not exist. So that's again mean value theorem. Okay, look at number 6 then. Got a dog called iPup on sale at 9 a.m., sold out within 8 hours. The number of customers in line is modeled by your values in the table. For t is between 0 and 8, what is the greatest number of intervals which Rolle's theorem guarantees the derivative equals 0? So Rolle's theorem has to be continuous, differentiable, and those endpoints have to be the same. The end values must be the same. So I don't have anywhere where another one is equal to 150. I don't have one where one's equal to 185. Don't have one with 135, but I do have one with 120. So I've got an interval here. And then I've got another interval here. So it looks like I've got 2 intervals where the derivative is going to equal 0 based on Rolle's theorem there. All right, let's look at question number 7 then. Particles moving in a straight line, we're given the velocity there. For which of the values is the particle speed? I'm sorry, the values of t is the particle speeding up. So, couple of things. One, remember that in order for speed to be increasing, for it to be speeding up, velocity and acceleration must share the same sign. One must be positive, one must be negative. So again, I'm going to use Desmos on this one. I'm switching us over. I'm going to go ahead and I'm going to put in the velocity equation. Let me put it in as v of x. That would be a little bit simpler. However, that's how Desmos will understand it. I know, crazy graph. Kind of cool, actually, right? And then I want to, let's find the value of v of pi over 6. Okay. Then I want v prime of pi over 6. Why did I want that? V prime gives me the acceleration. So now I'm deciding, do the velocity and the acceleration have the same sign? Yes. That means we are speeding up at pi over 6. Now, friends, that's using your calculator, right? To do that. Okay, let's check the next one. I'm going to put in v of pi over 3 and v prime of pi over 3. Do these share the same signs? No, they do not. And then finally, let's test 2 pi over 3. And these are both negative. So they share the same sign. So this is also a true statement. So D is going to be, oops, not D, forgive me. This is E. E, 1 and 3 is where the object's going to speed up because that's where the velocity and the acceleration share the same sign. All right. So we're about halfway there. So a particle starts at time t equals 0, moves along a number line so that the position is given here. For which of the following intervals is the particle always moving to the right? Okay, so since you have your calculator with this, let's go ahead and switch back over to Desmos. I'm going to put the position equation in here. Now remember, I'll have to do it. I can't do it x of t because Desmos only understands um, f of x or g of x or some name of x. So we'll have to use that. And then I've got x minus 6. All right, there we go. And we want to know where this is changing, always moving to the right. So we need to see the derivative because we know that the derivative, when the derivative is positive, then we know that the object is moving to the right. So I'm going to have it graph the derivative. And the derivative, notice, is in red. And we want to know when it's moving to the right. So we're looking for when this red is positive. You'll notice that starts at 5 and continues on. And so that's going to be my answer choice C right there. Okay, let's go ahead and switch back. Look at question number 9. I love this one because we were given all this number line work. So we were given the sign graphs or the number line graphs for the velocity and the acceleration. And which interval is the speed decreasing? So remember, speed decreasing is where the velocity and the acceleration have different signs. So look at it in this section, right? In this section, velocity is positive, acceleration is negative. So they have different signs. That's where we're going to have speed decreasing. That is between 0 and 1. All right. Then between 1 and 2, looks like they're both negative. Between 2 and 3, looks like velocity is negative, acceleration is positive. So we have another instance where the signs are different. And then from 3 and on, it looks like they're both positive. So it looks like we're looking for 3 and 4 only. And that would be answer choice D here. Okay, look at question 10. For what value of C is the instantaneous rate of change? That's code for derivative equal to the average rate of change. That's the slope the algebra way on the interval 1 to 4. So this is saying find a value of C where the derivative equals the slope of the secant line or the slope algebra way. Remember this y2 minus y1 over x2 minus x1. So let's find the derivative and we'll plug in C. I want you to think of this as 2 times x to the 1/2. So that would be 2 times 1/2 x to the negative 1/2. And then f of 4, that would be square root of 4, which is 2. 2 times 2 is 4. F of 1, square root of 1 is 1 times 2 is 2 over 3. So these cancel. I get 1 over the square root of x equals 2/3. Now I'm going to flip it both sides and multiply so that my equation becomes square root of x equals 3/2. Now let's square both sides. And I didn't plug in a C for it, but I could have. And that's where I would get answer choice D, that C is 9/4 here. All right, looking at question 11. On the graph of the derivative here, which of the following is true? So this is our derivative graph. F is increasing. So when the function is increasing, the derivative is positive. So is this graph positive from -1 to 5? -1 to 5, that's a yes. Okay. So the function has a point of inflection at x equals 2. The function has a point of inflection where the derivative has a max or min. So let's see if the derivative has a max or min at 2. Yes. Okay, last one. The function is concave up on x is less than 0 or between 2 and 4. So the function is concave up where the derivative is increasing. So is the derivative increasing from x being less than 0? Yes. Is the derivative increasing from 2 to 4? Yes. So this is also a yes. This is one of those ones where we get all 3 of our statements are true. I love in this question how you need to make the connections between the function and the first derivative. Make sure you go back to the video I did on the 10 commandment, or sorry, not 10, 5 commandments of particle motion. Those are going to be key to making those relationships work for you. All right, 3 more to go, friends. Number 12, the graph of the velocity is given. Which of the intervals is the acceleration negative? So acceleration would be the velocity's derivative. So this is really asking you on what intervals is the slope of this graph negative? So the slope of this graph between 0 and 10, slope here is positive. I'm looking for it to be negative. 35 to 45. From here to here, slope is negative. That works. How about from 15 to 35? From 15 to 35, Slope is positive, that doesn't work. So we're only looking at interval number 2 here. All right, number 13. Differentiable function, -2 to 7, such that the slope, the derivative equals 0 somewhere on that interval. If f of c is less than f of 7, then which of the following statements must be true? Okay, so only two rules that tell us, or two theorems that tell us values for the derivative. Rolle's theorem, which tells us the value for the derivative is 0 if your continuous differentiable and your endpoints are equal. Okay, so what it's telling you is basically by this first statement, Rolle's theorem is guaranteed. Okay, so the missing piece we haven't been told is that those endpoints have to be equal to each other. The endpoints must be equal to each other. So if we know that somewhere on this interval there's a y value that's less than that, okay, then we know that that must be the absolute minimum on that interval. So we know that either the absolute minimum happens at f of c or the absolute minimum happens at f of -2, the one we don't know. All right, number 14 then, our last one for this video here. Particle moves in a straight line. Its position is shown in this graph. The graph has a horizontal tangent at 1 and 5 and a point of inflection at 2. For what values is the velocity's particle increasing? Okay, so got position graph. You want to know when the velocity is increasing. So velocity is the derivative. You want to know when it's increasing. So you're going to need to know when the second derivative, the acceleration, you need to know when that's positive. Now, if the second derivative is positive, the function is concave up. Friends, that's a lot of connections, okay, that you've got to make because this problem doesn't require you to do any math. It's going to require you to do some analysis. And that analysis are those connections I just talked about. So if the velocity is going to be increasing, that means the acceleration has got to be positive. If the acceleration is positive, we know the function is concave up. So where is this graph concave up? Well, we were told there was a point of inflection at 2. That's important because we know concavity changes there. It is concave up here and then concave down after that. So we're concave up on this interval where t is between 0 and 2. Okay, I hope that helps with our questions. I hope I showed you some new things with Desmos. Definitely wanted to look at how do I analyze some of those questions that don't really require any math, right? And if you have questions or comments, please leave them in the comments below. I'd love the opportunity to help in any way that I can. Don't forget to hit the like and subscribe button. That way you get a notification every time a new video is posted. Bye-bye for now.